In this video, we're going to take a look at section 4.1 on basic concepts of probability. All right. So, the probability of an event is a number that indicates the proportion of times that event can be expected to occur, especially over several trials, right? So if you're conducting some kind of probabilistic procedure a multiple number of times, the probability of a certain event is the proportion of times that event can be expected to occur. It's not a guarantee. So for example, when you're flipping a coin, there's a 50% chance that it will be heads. There's a 50% chance that it'll be tails. So over the course of several coin flips, you can expect the proportion of times to get heads to be about half, right? 50% of the time. Again, it's not guaranteed to be exactly 50% of the time. There's some variation in the actual outcomes that you will get, but it's what you should expect to be the case, that half the time you'll get heads when you flip a coin, half the time you'll get tails. So it's the proportion of times that event can be expected to occur. All right, so that's what probability measures. That's what it indicates. Characteristics of probability. A probability is always a number between 0 and 1, inclusive, meaning it can equal 0 and it can also equal 1. So probability should be a number between 0 and 1 and can also either equal 0 or equal 1 in special cases. So those 0 and 1 are special probabilities. In fact, we're going to talk about them right now. A probability of 0 indicates an event that is impossible or cannot occur. And I'm not talking about unlikely. I mean literally, logically impossible. It cannot happen under any circumstances. Sometimes I'll give a scenario that's unlikely. It's very rare, but it isn't technically 0. And I can't think of one off the top of my head right now. But it has to be impossible for the probability to be 0. A probability of 1 indicates an event that is certain to occur and cannot be avoided under any circumstances. So when a procedure is run, this event, if it has a probability of 1, has to happen. There's no other way around it. So for example, when you roll a dice, like a 6-sided dice, the probability of getting a number between 1 and 6 is 100% when you roll a dice, a 6-sided dice. Right? You have to get a number between 1 and 6, including 1 or including 6, right? So the probability of getting a 1, 2, 3, 4, 5, or 6 when you roll a 6-sided dice is 100%. You have to get one of those numbers. So in that case, the probability is indicated by the number 1, which is 100%. Otherwise, most probabilities will fall between 0 and 1. So you might have a probability of like 0.25. That's 25%. That's a 1 in 4 chance. Those are, more common types of probabilities. But 0 and 1 are special cases. Most probabilities will be somewhere between 0 and 1. So what you should realize from this screen is that a probability cannot be negative. It doesn't make sense to have a negative probability, and a probability cannot be bigger than 1 either. So if somebody says the probability of this happening is 2.5, that's nonsense. That doesn't make any sense whatsoever. You can't have a probability equal to 2.5. It has to be between 0 and 1. Okay. An event is, so I guess I have a typo here. I apologize for that. So I'm kind of constructing these presentations right before recording. So these have not been tested in the wild where I'd usually spot these kind of typos. So I apologize. An event is any collection of results or outcomes from a procedure, right? So for example, a procedure could be flipping a coin, right? And an event from that procedure would be getting heads or getting tails when you flip a coin. Rolling a dice would be another example of a procedure. And an event in that case could be rolling a 1, rolling a 5. You could also characterize an event as rolling an even number. So it doesn't have to be specifically the numbers on the dice that are an event. We could get more complex in our description of events. We could say rolling a number that's at least a 4, right? 4, 5, or 6. that would be considered an event from the procedure of rolling a dice. However, a simple event is an outcome or event that cannot be further broken down into simpler components. So rolling an even number with the dice is not a simple event, because rolling an even number can be broken down to specifically rolling a 2, a 4, or a 6, right? And rolling a 2, that is a simple event because that cannot be broken down into any further simpler events. So rolling a 2 is as basic as you can get with rolling a dice. So rolling a 2 would be a simple event, right? Flipping a coin and getting heads. Heads would be a simple event. Tails would be a simple event. The sample space for a procedure consists of all of the set, I'm misreading here. The sample space for a procedure consists of the set of all possible simple events. So the sample space is a collection of everything that could possibly happen from running that procedure in terms of just the simple events. So for rolling a dice, the sample space would be 1, 2, 3, 4, 5, 6. Those are all the possible simple events that can happen when you roll a 6-sided dice. For flipping a coin, the sample space is much simpler. So if you're just going to flip a coin once, the sample space would be heads or tails, right? That's it. That's the only two things that can happen when you flip a coin, right? And that would be our sample space for that particular procedure. All right. So here's some notation that we use when we do probability calculations. A capital P denotes probability. So when you say P equals this number, you're saying the probability is equal to this number. A, B, and C are often used to represent specific events of a procedure. I typically avoid using those, and I just write the actual event itself rather than letting A represent it. But it's a common practice. So you don't have to write the same event over and over and over, writing it out in words. You just say, let A be the event of getting heads when you flip a coin. And then from that point on, you can just use A whenever you want to talk about heads from flipping a coin. You can say, let B be the event of getting tails from flipping a coin. And then you can just use B to represent tails from that point on, right? And so you put those together. And so if you want to talk about the probability of event A, there's the notation for that right here, right? The probability of event A occurring can be denoted this way. So P of A, it's function notation. So I think I've mentioned this already in previous videos, but college algebra is a prerequisite for statistics. And here's another case of something that you would have seen in college algebra that we're using here in statistics. And I like to point those out whenever those come up. And that is function notation, even though I don't know if this technically would be a function. I guess so. I guess probability is a function, actually. So we use function notation to denote the probability of certain events. So the probability of event A is P of A, and that denotes the probability of event A occurring. I'm sorry you couldn't see that last word there. So, all right, so that's notation that we'll use throughout chapter 4. Okay, so let's move on to the next topic. All right, so here's an example. Let the procedure be rolling a 6-sided dice. Let A be the event of rolling a 2. So what are the simple events from rolling a dice? I kind of already gave this away, right? This would be 1, 2, 3, 4, 5, and 6. So those would be all of the simple events from rolling a 6-sided dice. That collection is our sample space. So I don't know, I feel a little bit redundant here putting both of these. So the sample space would be this collection of events. So here are all the simple events that could occur. To write that as a sample space, you would put these curly braces around it, and that makes it into a set. That's the notation we use for sets in mathematics. And so we have this set of events that make up our sample space. And so I would say, I don't know, I don't feel like writing out the numbers again, so I'm being kind of lazy. So this would be our sample space here. So what's the probability of A occurring? What's the probability of rolling a 2 when you roll a 6-sided dice? Most students have a pretty good feel for determining these probabilities when things are still simple enough. Now it gets more complex, and I was just realizing, that another type of scenario I like to look at with probability is flipping a coin multiple times. So let's say we're going to flip a coin 3 times. What's the probability of getting 2 heads out of 3 coin flips or something like that? Those get a little bit more difficult to calculate, and students really begin to struggle when you start compounding these events. So if it's a simple thing like flipping a coin or rolling a single dice, that's not too hard to figure out. But if you're going to roll 2 dice, or if you're going to flip 3 coins, that's when things start to get more complicated and students start to have trouble intuiting the probabilities at that point. So the way you would calculate the probability here, and we're going to actually formalize this in just a minute, but you look at how many ways can you roll a 2 when you roll a 6-sided dice. There's only one outcome where a 2 is rolled. And so there's only one way to get a 2, so there's only one way for that to happen out of 6 possible outcomes. All right, so we have 6 possible outcomes when you roll a 6-sided dice. Now, sometimes students will make the comment, like if you flip a coin, it's either heads or tails, right? But sometimes students will say, well, sometimes it's really rare, but maybe the coin could just land on its edge. So we don't consider that as a possible outcome. So with the dice roll, you might say something to that effect, like maybe you roll the dice and it lands in a weird way where you don't get a conclusion or something like that. But then we just don't count those dice rolls. That doesn't. So when we roll a dice, it only counts if it lands with a certain face up, and that's going to be the outcome from rolling the dice. In those circumstances, there's only 6 possible outcomes, and only one of those gives you a 2. So the probability of rolling a 2 with a 6-sided dice would be 1 out of 6. Right. There's one way to roll a 2 out of 6 possible outcomes, so the probability is 1/6. It's a number between 0 and 1. As a percent, so a lot of people like to think of probabilities as percent, but you'll find it's more convenient mathematically as we go through chapter 4 to actually just leave your probabilities in fraction form or decimal form if the decimal isn't like a run-on decimal. In either case, I would recommend following the directions on my stat lab. So if the directions say to write the answer as a fraction, then just leave it as 1/6. If the directions specifically say to write the answer in decimal form, you'll want to plug that into your calculator. And I feel like I should know 1/6 off the top of my head, but I'm feeling uncertain of myself right now for some reason. So I'll do this in my calculator. 1 divided by 6. Yeah, okay, so it's 0.1666. Just repeating 6s after that point, actually. And so if we wanted to write this in decimal form, it'd be 0.16. And since the 6s repeat, we're going to stop after 3 decimal places, and it'll round up. So it'll be 0.167 in decimal form. And usually if they want decimal form, they'll be specific, round to this many decimal places on my stat lab. But we do have a rule of thumb we'll talk about later in the video, but you should just go by the directions when you're doing the homework. And as a percent, this would be 16.7%. So there's a 16.7% chance, but you will find most often they don't want the answer as a percent, even though that might be more familiar to us. They'll want the answer as a fraction or as a decimal. And so I would just leave it as one of these 2 forms. All right, so the basic rules for computing probability. We're going to be looking at more complex probability questions later in the chapter. But for this section, we're going to just be very straightforward and just ask, what's the probability of this singular event happening? And here are the ways you could calculate those probabilities. You can, if necessary, calculate a probability experimentally. So we have the experimental rule for calculating probability, which we're not really going to take advantage of in this class. We are going to be using the second one there, which is the theoretical rule for calculating probability, which is what we just did for calculating the probability of rolling a 2 with a 6-sided dice. That was a theoretical calculation. We did not calculate that experimentally. And then there's subjective. You can calculate a probability subjectively. It's probably the worst one of the 3 as far as like the reliability of that calculation, because it's subjective, right? Different people would come up with different answers depending on what factors they chose to consider and how they weighted those factors and the numbers they assigned to those factors. And people will get different answers depending on that. And you really have to be an expert in that area in order to do that kind of subjective calculation. And so It's not a method that we will be using at all, but just to make you aware that some probabilities are calculated in a subjective way. All right, so for experimental calculations, the way you calculate a probability experimentally is you take the procedure that's being described and run that procedure a certain number of times. I'm assigning the letter n to that. But the more you run that procedure, the better your experimental probability will calculate the actual probability. We have a name for that rule. So the more often you run the procedure, the better estimate you get for the actual probability of whatever it is you're trying to calculate the probability of. So you run the given procedure n times, and then you count the number of times that event A actually occurs in those n procedures that you run. And then the formula for calculating the probability experimentally is to take the number of times that A occurred in your experiment divided by the number of times you ran the procedure, which is n. Right? So how many times did event A happen divided by the number of times you ran a procedure? In my face-to-face classes, what I would do is I would take a thumbtack, which has like a rounded back to it, and I would toss it into a bucket. And and the probability we were trying to calculate is what's the probability, not how many times, but what's the probability that when you throw the thumbtack into the bucket, that it lands with the pointy end up rather than laying on its side, sideways. And that is something you can't really calculate theoretically, because the theoretical calculation would really probably be more subjective anyways, would be to take into account the velocity at which you're throwing it in the bucket, the friction of the surfaces. It'd be too complex to calculate in theory. And like I said, that really would almost become a subjective calculation, because you'd have to kind of subjectively decide what things count and to what degree they should count and what numbers to assign to those different probabilities to get the theoretical calculation. So in that kind of scenario, the best way to calculate the probability of the thumbtack landing with its pointy end up is to do experiments. So this is what we would do in class, is I would take the thumbtack, throw it into the bucket. I didn't want to sit there and do that for half an hour, so I didn't do a large number of those procedures. I would just run the procedure like 20 times, throw the thumbtack into the bucket 20 different times, and then we would count how many times did it land pointy end up. And then from that, we would get a probability. We take the number of times it landed pointy end up, divided by the number of times I threw the thumbtack, to estimate the probability of that event occurring. And running it 20 times gives us one estimate. If we ran the procedure 50 times, we would get a different estimate, which would really be a better estimate, because the more often you run the procedure, the better your estimate's going to become for that probability. So I'm not going to actually run an experiment for you guys, but you could also do experimental probability to confirm theoretical probabilities, right? So what's the probability when I flip a coin that I get heads? We know it's a 1 out of 2 chance, right? It's a 50-50 thing. So it's a 50% chance that I would get heads. But we could try to confirm that experimentally by flipping a coin a bunch of times. So we'd flip a coin, 50 times, 100 times, and count how many times am I going to get heads? How many times do I get heads from flipping a coin 100 times? And then calculate the probability that way to make sure that it's close to that 50% mark that we would expect. So if you suspect, for example, that you have a coin that's not fair, that's weighted more to one side than the other, this is how you might confirm whether that's actually true. Take the coin you have, flip it 100 times, and if you're getting heads only 30% of the time, there's something wrong with that coin, because it really, we know in theory, should be closer to 50%. And so that coin seems to be weighted in such a way that you're getting heads less often than you should. All right, so that's how experimental probability works, just to make you aware of it, but it's not really something that we will be making use of in this class. We're going to be sticking with theoretical probability, which we're going to talk about in just a second. I already kind of mentioned this, the law of large numbers. That's the name for the thing I mentioned earlier. As a procedure is repeated again and again, the experimentally determined probability of an event tends to approach the actual theoretical probability. So the more often you run the procedure, the better your estimate becomes for the probability of that event. And that's when you're doing experimental probability. So the more often you do it, the better your estimate becomes. Here's the theoretical rule for calculating probabilities, but it does depend on a couple of assumptions in order for this calculation to work. So assuming that a given procedure has n different simple events, like with rolling the dice, there were 6 different simple events, and each simple event has an equal chance of occurring. And so that's a big assumption that we're making there, and not every situation we encounter will have simple events that all have an equal chance of occurring. So again, that means it has to be random, right? The chance of getting a 1, 2, 3, 4, 5, or 6 has to be, the number we end up getting from our dice has to be random in order for this theoretical rule to work. Each simple event has to have an equal chance of occurring when we roll the dice. So in that case, you can calculate the theoretical probability by taking the number of ways that A can occur divided by the total number of simple events that are possible with that procedure. And that gives you the theoretical probability. So going back to the dice example, how many ways could we roll a 2? There's only one way for that to happen, so the numerator is a 1. Out of how many different possible outcomes when you roll a 6-sided dice? There were 6, right? 6 different simple events that were possible. And so we get 1 out of 6 as the probability of rolling a 2, which is also the probability of rolling a 3 and rolling a 4. They each have a 1/6 chance of occurring. All right, and so that's how you do theoretical probability, and that's what we're going to do for most of our problems. There may be a couple of problems where it's experimental probability, and they give you but they're not going to make you do the experiment because the results would vary each time. They give you the results of the experiment, and you would just basically do the same thing you do for theoretical probability. How many ways did it happen divided by how many times did we run the procedure? But they'll give you those numbers instead of making you do the experiment yourself. All right. The one we probably will never use, and not even in the homework, is subjective probability, where you estimate the probability of event A occurring by using knowledge and estimates relevant to the circumstances. So one scenario that I like to bring up for using subjective probability is, what if we wanted to calculate the probability of a meteor hitting your house? So a meteor is an object that falls from space through the atmosphere and actually reaches the earth, right? It reaches the ground. What is the chance that a meteor strikes your household where you live? It's not 0. It's very, very unlikely to happen, but it isn't 0. It happens occasionally, right? There are reports of people who are just sitting in their house minding their own business and a rock crashes through their roof, right? It doesn't happen very often, but it does happen. So it's not 0, because 0 means it would be impossible, and this is not impossible. So, but how would I calculate that? I can't really do experiments, right? How would I confirm that probability experimentally? I can't go into space and start throwing rocks at the earth and seeing how many hit a house, right? That's how you would do that experimentally, and that's not viable. That's not possible. How do I calculate that theoretically speaking? I'd have to take into account how many rocks are floating out in space, how many crash into the atmosphere, how many actually make it to the earth, how many land in the ocean versus on land, what proportion of land is occupied by houses, right? All of those would have to be considered, which is how you would do subjective rule, but you're going to do estimates for all that. So instead of doing it theoretically with precise calculations, and also, the theoretical probability we talked about require that each event has an equal chance of occurring, and there's just no way to guarantee that with meteors crashing into the earth. So subjective would be the way you would try to calculate that. And you would want to get expert opinions on, how often do meteors crash land to the earth? What proportion of the Earth's surface is occupied by houses, right? And that would give you, and from that you get a proportion of, the ratio of the number of, the area of the Earth that's occupied by houses versus the area that's not occupied by houses. And you have to take that into account when you're doing the calculation. And if you ask different experts to do this calculation, you might get different answers because they might assign different values to those different estimates, right? But that's how subjective probability works. And you would do that for cases where experimental and theoretical probabilities are not an option, right? This is really sort of last resort. Okay. Another topic, and we're going to get to some examples here in a minute, but I just want to kind of get all the concepts out of the way first, is the complement, which I should have underlined here. I apologize. Again, another typo on my part. I'll try to underline it now, but it's really hard to draw straight lines on this thing. The complement of event A consist of all outcomes in which the event A does not occur. So the complement of A is all the ways A does not happen. And we denote the complement as, the complement of event A is A with a bar over the top of it. And this just means, in logic, because this is actually notation that's used in logic, it means not A. So it's all the ways A does not happen. And there's a mathematical relationship between the probability of A occurring and the probability of A not occurring, and it's given by this formula right here. Right. So the probability that A does not occur is equal to 1 minus the probability that A does occur. And so if you are asked to find the probability of, for example, not rolling a 2, it might be easier to calculate first the probability of rolling a 2 and then take 1 minus that in order to find the probability of not rolling a 2. So the probability when I roll a dice of not rolling a 2 is 1 minus the probability of rolling a 2. And we already did that calculation, and it's a more straightforward calculation, right? There's less things to count. How many ways can we roll a 2? There's only one way for that to happen out of 6 possibilities. So the probability of not rolling a 2 is going to be 1 minus that probability. It'll be 1 minus 1/6. And it does involve a fraction, unfortunately. So that might be one drawback to doing it this way, because now you have to do a calculation with a fraction, but it ends up being 5/6. Right? So you just think of this as 1 over 1, get a common denominator, which will be 6. And so you end up getting 6 over 6 minus 1 over 6. That's going to be 5 over 6. So that's how you might calculate the probability of not rolling a 2. Now, for this example, it's pretty easy just to calculate how many ways would I not roll a 2. There's 5, right? There's 5 outcomes where I'm not rolling a 2 out of 6 possible outcomes altogether. And so you could just kind of calculate it directly. How many ways does that happen divided by the total number of possibilities? The number of ways of not rolling a 2 is 5. There's 5 ways that happens out of 6 possibilities. But there are definitely going to be problems where finding the probability of something not happening would be very difficult to count up. And so it's easier to find the probability that the thing actually does happen, because that's easier to count up, and then do 1 minus that probability to get the probability of that thing not happening. So hopefully we'll have an example of that at some point. Okay. The round-off rule, express probabilities as exact fractions or decimals, or for run-on decimals, round off final decimal results to 3 significant digits. That isn't the same as 3 decimal places. While this is our rule of thumb that we want to follow, on MyStatLab, you should just follow the directions, and they don't actually usually say use 3 significant digits on MyStatLab. They normally will say round this to 3 decimal places or round it to 5 decimal places, or they'll be very specific about how to round that. But if in the absence of directions, like if I give you an exam and on the exam I don't say how to round that probability, then you should follow this rule of thumb. Round it to 3 significant digits, which is the number of digits after the initial string of zeros, right? So 0.001 only has 1 significant digit. The zeros here don't count as significant digits. They're really just placeholders. So 1 becomes your first significant digit. So this only has 1 significant digit here. Right. So even though that's 3 decimal places, this was only rounded to 1 significant digit, which is not the round-off rule. So if we get a number like 0.001379021, something like this, if you round it to 3 decimal places, this is what you would get, but that's only 1 significant digit because those first 2 zeros don't count as significant digits. So to round this to 3 significant digits, which is what the rule of thumb is, I would want to, so this counts as the first significant digit. Once you hit that first significant digit, everything after it is a significant digit, whether it's 0 or not. So this 0 here counts as a significant digit. It's just the initial string of zeros that don't count. Once you hit that first non-zero digit, that becomes your first significant digit, and everything after it will be significant as well. So So to round this to 3 significant digits means I want to round it to here. This is 1, 2, 3. That's 3 significant digits there. The 9 tells me to round that up to an 8. So this would be 0.00138. That's 3 significant digits, and that's following this rule of thumb. All right. Significant digits can be very important in like a science class. So maybe you've already encountered this topic in like a chemistry or some other kind of science class where, significant digits are important for presenting data that is, reflective of the precision and accuracy of the measurements that were involved. All right. Now here's one that is really kind of an important thing to understand, because while this description sounds subjective, it sounds like an opinion, we have a very precise definition of what we mean by this. So if we say an event is unlikely, that sounds like it's an opinion, right? If I say, oh, that event was unlikely, get my words scrambled up. If I say that event is unlikely, it sounds like I'm just giving you my opinion on that event. But in this class, we actually have a very precise definition of what we mean by unlikely. And so we don't just throw that term out there when we have an opinion that something is kind of rare. We mean something very specific here. So we say an event is unlikely if its probability is very small, and we generally regard that to be anything that's 5% or less. So 0.05, which is 5% or less, that is a small probability. And in that case, we will say that event is unlikely. If it's more than 5%, that's not small enough to be considered unlikely. So a lot of students will have the opinion of, like, if the probability is 10%, they'll say, oh, that's unlikely, 10%. Not by our rule of thumb here. So 10% really isn't that unlikely. It happens 1 out of every 10 times, which is pretty frequently. 5% is 1 out of every 20 times. That's when we're going to start considering things to be unlikely. So anything that's 5% or less, then you can call that event unlikely. If it's more than 5%, do not use that description for it. It's not unlikely if it's higher than 5%. All right. So we have to so we're all on the same page when we use that term. We want to have a good definition for when that term gets applied. So when I say something's unlikely and you say something's unlikely, we kind of both have the same idea in mind. If we're not specific about that, then when you say unlikely, I'm thinking you mean less than 5%, but you might be thinking less than 10%, and then we have that confusion about what unlikely actually means when we use that word. So it kind of makes it ineffective or useless if we don't agree on what that term actually means. All right, so here are some examples. What is the probability of rolling a 7 with a fair 6-sided dice? The probability is 0. It's impossible, right? When you're rolling a 6-sided dice, the only outcomes that are possible are 1, 2, 3, 4, 5, and 6. 7 is not a possible outcome from rolling a 6-sided dice. So here the probability would be 0. What is the probability of rolling at least a 1 with a fair 6-sided dice? Now, I want to kind of introduce you to this terminology of at least. At least means that much or more. At least really means greater than or equal to. It's weird because the word least is in there, but think about the example I always like to give is at the fair. You might see a sign that says you have to be at least this tall to ride this ride. What does at least mean? It means you have to be that tall or taller, that much or more, right? So at least actually means greater than or equal to that number. So what is the probability of when you roll a dice that you get greater than or equal to 1 on that dice roll? It's certain to occur. It has to happen, right? Because when you roll a dice, you're either going to get a 1, 2, 3, 4, 5, or 6. So it has to be at least a 1, right? It has to be 1 or more. It's going to be 1 all the way up to 6. And so it's certain to occur. It's unavoidable. When I roll a dice, I will at least get a 1 on that dice roll, right? I can't avoid that. So that has a probability of 1. And so those are examples of the extreme cases of impossibility and certainty, right? And again, it has to be complete. It can't be just, what are the chances that if I were to hit a baseball with a baseball bat that I would hit a home run? It's practically 0, right? It's very, very unlikely. I would like to say for myself that there's no chance of that happening. But when I say there's no chance of that happening, I'm speaking more informally. There really is a probability that when I hit a baseball, it will go out of the park, right? There's a chance that can happen. It's just very, very unlikely because I don't have the skills to hit the ball that well. But it could still happen, right? And so it's not zero. Even if I might say there's no chance that I would be able to do that, it's still not technically zero in that case, right? Zero means it has to be actually impossible. And it's not impossible. When I hit the ball, there is a chance I might hit it over the fence, right? And the same thing, now this one's a little bit maybe unfair, but, so I've asked students on the test, give me an example of an event that has a probability of 0. And this would be a great example. Rolling a 6-sided dice and getting a 7. That is logically impossible. But what I'll get from students sometimes are things like, they'll say, the chance of me, they'll like one I think of off the top of my head is like, the sun will rise in the east, has a probability of 1, right? It's certain to occur that the sun will rise in the east. And I don't want to be like dark or negative or anything, but like there's a chance that might not happen sometime, right? I mean, like if the earth got knocked sideways or, the sun explode. I mean, like in the future, when the sun dies out, it's not going to be rising in the east anymore, right? Or for example, given long enough time, the earth becomes tidally locked with the sun, where the sun, like the same face of the earth, how do I want to say this? The same side of the earth will face the sun all the time, right? And so then there won't be any sunrise or sunset at all. And that will happen eventually. It'll take I think the sun's going to die first before that would happen. But, like the moon is tidally locked with the earth, right? That the earth and the sun are going to end up in that configuration as well eventually if you gave it enough time. Anyways, in my mind, I think that's not 100% certain, right? There are physical situations where the sun might not rise in the east anymore, right? If the earth stops rotating or if the sun goes away, which are very, very unlikely to happen, but could still happen. So I really look for examples where there's just logically no chance of something occurring to get a probability of 0, or logically things that have to happen in order to get a probability of 1. But I usually give students credit for those examples because I think they have the right idea, right? That it always happens that the sun rises in the east. So experimentally speaking, it's 100%, right? Because we've done the experiment multiple times and every day the sun rises in the east. So it happens 100% of the time from our experiment. So I go ahead and let that go. But, you kind of want to think of things like that. Like, is there some way where this might not happen? And if there is, then it's not 100%, right? Because there's some way where the thing might not occur. And so that takes away from that probability. So anyways, kind of going off the trail there a little bit. So let's get back on track. On a multiple choice test with options A, B, C, and D, and only one correct answer, what is the probability of randomly guessing the correct answer? So let's say it's a problem I don't know anything about. I'm just going to randomly guess A, B, C, or D. One of them is right. What's the probability that I pick the one that's right? So you do the theoretical calculation. How many ways can it occur divided by the total number of possibilities? So the probability of getting the correct answer, well, how many ways could I choose the correct answer? There's only one way, and that's to pick the one that's right. Now, we don't know which answer is actually the correct answer, but let's say hypothetically the correct answer is B. So there's only one way I could choose B as my answer by bubbling in the B out of 4 different possibilities, right? There's 4 answers I could choose from, but only one of them is correct. So I have a 1 in 4 chance of choosing the correct answer. All right, and so that's the probability there. So if you do that for the entire test, just guessing, you're likely to get about 25% of them correct, right? Because each time you have a 25% chance of getting the right answer. So over the entire length of the test, you should get about 25% of them correct on average, but sometimes you might be a little lower or a little higher, which means it's not a very good test taking strategy, right? Because if you're only guessing throughout the entire test, if you didn't study and you just make guesses, your test score is going to be about 25% or so. 14 out of 50 tires in an inventory are known to be defective, right? So they know this. They have 50 tires. They know 14 of them are defective already. What is the probability that if they select one of those tires at random, that it is not defective. So notice I capitalize, that's for emphasis here. We want to find the probability of getting a tire that's not defective. And you could calculate this because the number we're given here is the number that are defective out of 50. We know 14 of them are defective, but I want to find the probability of getting one that's not defective. And you could calculate how many of these are not defective by subtracting, right? There's 50 tires altogether, minus the 14 that are defective, and you'll find out how many are not defective. But we could also use the complement rule here, that the probability of finding one that's not defective is 1 minus the probability of finding a tire that is defective. And that is going to be easier to calculate because that's the number I was given, right? So what's the probability of, if I pick a tire at random, that it's defective? Well, there's 14 ways I could choose a defective tire, right? There's 14 different tires that are defective. So there's 14 different tires I could pick that would fit that description out of 50 tires altogether. And that's the probability of getting a defective tire. So to find the probability of getting a tire that is not defective, I will take 1 minus that because these are complements, right? They're opposites of each other, right? That's what complement means. I don't know. I felt like there was more I wanted to say there, but I couldn't think of any way to expound on that. So we'll take 1 minus this, which if you have a calculator that will do that calculation for you, go ahead and do that. I'm going to go ahead and do it by hand. So I'll think of this as 1 over 1. Get a common denominator, which is 50. So this will become 50 over 50 minus 14 over 50. And you see that ultimately anyways, you end up still having to do that subtraction, right? Because this is going to be 50 minus 14, which is what I suggested you could have done up here at the beginning if you wanted to calculate it the other way. But this kind of walks us through it anyways, without having to think of it that way. So anyways, we get 50 minus 14, which is 40, 30, 36, right? So we get 36 out of 50. Now with probabilities, we're not as picky about reducing. This one, I'm going to say, let's go ahead and reduce because the numbers are easy enough to work with. But if you get like a probability, and this will happen because we'll have some like big numbers sometimes. So let's say your probability is like 580 over 1024, right? That could be reduced because they're both even, but it's not really worth reducing with those big numbers. You'll reduce it to something else, which will probably still have some fairly big numbers, and you're no better off than you were with the original fraction. So with probabilities, we're not as picky about having to reduce those fractions, unless it's something really obvious like 2 over 4, that reduces to 1/2. I'm going to go ahead and reduce this by dividing a 2 out from the top and the bottom. And we're going to get 18 over 25, which again, isn't much more illuminating than 36 over 50, right? But that is the fraction in reduced form. Okay, so 18 out of 25. And if you feel like that bugs you, like I still don't have a good sense of what that probability is, you could always convert this to decimal form. And let's see what we get. So I think we'll get a nice answer anyway. So you get 0.72. Is that right? Yeah, 0.72. Yep. So 0.72, which gives you a better idea because that means 72%. So if you're going to pick a tire at random out of those 50 tires, there's a 72% chance that you will get one that is not defective. All right. Okay, so here's a big paragraph. In a recent year, 281 out of 290,789,000 people in the United States were struck by lightning. So 281 out of that big number. Estimate the probability. So this is kind of an experimental one, actually, right? Because this was taken from a given year, calculating how many people got struck by lightning that year out of the number of people in the United States. Estimate the probability that a randomly selected person in the U.S. will be struck by lightning this year. So the experimental probability, so like I said, you might have some problems with experimental probability. The probability of getting struck, I'm just going to put struck here, is going to be the number of ways, not the number of ways, but the number of times it happened divided by the total number of procedures run. Now, this time the procedures are just the number of people. So we're assuming that everybody was an experiment. And we ran these 290 million people out in the open. I guess we didn't really run them out in the open, but we just let them behave as usual throughout the entire year. And we saw that 281 of those people actually ended up getting struck by lightning. So think of each person as the procedure, that each person is the experiment that we're running. And we see how many times they got struck by lightning out of the number of people that we were experimenting on, right? And so we have 281 people that were struck by lightning out of 290,789, saying the wrong number, 290,789,000 people that were part of the experiment. And so this, again, maybe it could reduce, but it would be silly to reduce a fraction like this because it's not going to make it any more useful to us for understanding. What might be more useful, again, is a decimal. So we'll take 281 divided by 290,789,000. And we get a ridiculously small number, 0.00. I have to count the zeros here. 1, 2, 3, 4, 5, 6. 6 zeros. And then we have 97. And my calculator, that's where it stops. Maybe if I turn it sideways, I'll get more. Let's see. Oh, I get a little bit more. 966. So let me undo that 7. Because remember, we want to do 3 significant digits. Right? That's only 2. Right? Because all of these zeros don't count as significant digits. This is my first significant digit. And I need 2 more after that to have 3 altogether. So I have 966. And then the number after that was a 3, which I don't need, but that tells me to round this down to a 6. So I don't round it up to a 7. And so this would be my probability to 3 significant digits using that rule of thumb. All right. And so is this unlikely? Yes. This is less than 0.05. It's less than 5%. And so this means it's unlikely to get struck by lightning. It's unlikely for a person. So if this experimental probability is a good estimate for the actual probability, it is very unlikely that a person will get struck by lightning throughout the year, right? Is a golfer reasoning correctly if he or she is caught in a thunderstorm and does not seek shelter from lightning because the probability of being struck is small? You might think so, because you might say, the golfer might say, well, the chance that I would get struck by lightning now is 0.00000966, right? Way, way less than 1% chance of getting struck by lightning. So I don't need to worry about it. The reason that reasoning is bad is because if you happen to be one of the rare people to get struck by lightning, that's catastrophic. That's deadly. You could die from that. So even though it's a small risk, you want to take that risk seriously because the consequences of not taking it seriously are so severe. Now, if this was something to do with like stubbing your toe, then maybe you don't worry about the risk so much. Because if you stub your toe, okay, you're in pain for a couple days and it's no big deal. So if avoiding a certain, if the chance of you stubbing your toe was this small, but how do I want to describe this? I'm having trouble thinking of what I'm trying to say. If we're talking about a scenario where the consequences are not so severe and the effort to avoid the scenario would be significant, but the consequences are not severe, then maybe you don't worry about it. So, because to, stop your golf game, to seek shelter, that takes some effort, right? If it was about stubbing your toe, then maybe it's not worth taking that effort to avoid stubbing your toe because it's unlikely to happen. And even if it does happen, not a big deal, not a big consequence. You just, like I said, you're in pain for a couple of days, but otherwise you're going to be fine. But getting struck by lightning is a big consequence. So you have to kind of weigh that as well. Not just what are the odds of this happening, but even if I somehow experience, it's unlikely to happen, but if it does happen, even though it's unlikely, it's catastrophic, it's deadly, right? So you want to avoid that even if it's a rare occurrence. And it's worth taking the effort because of the severity of the consequences, right? Even though it's a small probability. Hopefully that makes sense, what I just said. All right. Adults were randomly selected for a Newsweek poll, and they were asked if they favor or oppose using federal tax dollars to fund medical research using stem cells obtained from human embryos. Of the adults selected, 481 were in favor, 401 were opposed, and 120 were unsure. Based on these results, find the probability that a randomly selected adult would respond unsure. Is it unusual for an adult to be unsure? All right, So this one's kind of tricky. Now, I think we're given a little bit of a clue here by having 3 different numbers, which was kind of nice for them to do. So if there wasn't the unsure option, and we just had these 2 numbers, either you're in favor or you're opposed, and I ask you, what's the probability that if we pick a person that they were opposed? A very common mistake students would make is they would say, well, 401 were opposed, and there's 481 right here. And they would divide those 2, and that'd be their probability. But that is not the correct denominator, right? The 401 is the correct numerator, right? So how many ways could you choose a person that was opposed? There are 401 ways to do that. But the denominator is supposed to be out of the total number of people that you could choose from. And there isn't just 481 people that you could choose from. There were 481 people who were in favor of the proposal, but that's not the total number of people altogether. So to get the total number, we actually weren't given that information. We have to calculate it, right? So by having 3 numbers here, hopefully that really makes you positive, because if there's only 2, it's very common for students to make that mistake. They take the smaller number and put it on top, the bigger number on the bottom. But that is not the correct answer here, because the bigger number is not the total number of people in the survey. The bigger number is just the number that said they were in favor, right? So we need to find n is what I'm trying to say. Now, because we have 3 numbers here, you have to make a choice, right? Because we know 120 is supposed to be on top, right? So the probability of finding somebody who's unsure, well, there's 120 people we could choose from that were unsure. But the denominator should be the total number of people that we could choose from altogether. And now you have 2 other numbers to think about, and that should make you think, well, which number do I use? Well, it's not that you use either of these numbers. You want to find the total number of people in the survey, which means you need to add those numbers up. So n is going to be, well, we had 481 people that said they were in favor. We had 401 that were opposed. And you have to add in the 120 that were unsure to get the total number of people that were a part of this survey. So sometimes they won't tell you the total number of people that you could choose from. You have to calculate it by adding up all the people that were involved in the data, right? And so I'm going to go ahead and add this up on my calculator. So I have, let's clear this out, let's start with the first number, 481 plus 401 plus 120. And so there were 1,002 people in the survey altogether. So there's 120 people that said they were unsure that we could select. So how many ways could we pick somebody that was unsure? There's 120 people that said that. So that's the numerator. Out of how many people could we have chosen altogether? 1,002. Right, and so that's how you calculate that probability. So be careful about, don't just take the numbers you see in the problem and try to make them work for your calculation. Make sure the numbers are the numbers that you actually need for your calculation. The number of ways it could happen, the number of ways we could choose somebody that's unsure, divided by the total number of people that we could choose from. And this time we had to calculate the total number of people that were involved in this survey, the total number of people that data was collected from, right? So 120. Again, we could leave it as a fraction. So I should say that this is a perfectly fine answer. On MathXL, it may be, I keep saying MathXL. On MyStatLab, this could be the way they want the answer. It might say, type your answer as a fraction, and this is what you would type in. If it requires you, and if it says fraction or decimal, just leave it as a fraction, right? You already have the answer. Why do more work? If fraction is good enough, just leave it as this fraction. If the directions say you have to type it as a decimal, it's going to be 0.11, okay, sorry. Well, here, I'll just write down what I got here. 0.11976, there's more to it than that. But if I'm going to go 3 significant digits, that means I want to stop here, which means I'm going to round it based on this number. That's a 7, so I round that up. Since it's a 9, it rolls over to 0, which bumps the next place value up to a 2, right? And so we get 0.120 in that case. And you might say, oh, that's just 0.12. No, you want to keep the 0 there to show that you perform this calculation out to the 3rd significant digit. If you write it as 0.12, it will be assumed that you only kept 2 significant digits, but you didn't. You kept 3 significant digits, and so that 0 is significant. You need to keep it there to indicate that you calculated it out to 3 significant digits. If you write it like this, that's only 2 significant digits, and that's what people would assume about your answer. All right, so keep the 0 there. Okay. Let's see. I got one, two. I got a few more examples. It looks like. Sorry. What are we at? We're at 55 minutes already. Oh gosh. Okay. Consider the situation in which you will roll 2 dice, one red and one blue. And I like to give them different colors because when they're the same color, they're indistinguishable, and that confuses the situation. There are 2 distinct dice here. Even if in reality, like when we're playing Monopoly, right, our 2 dice are the same color. And we don't know which one's which. But really, there are 2 distinct dice there. And one of them's giving you one number, and one of them's giving you another number. By color coding them, that really drives the point home. So imagine if with Monopoly you had a red dice and a blue dice, right? Then you'd be aware that, when you get a 7, for example, you might get a 4 on the red dice and a 3 on the blue dice. That's one way of getting a 7. But you could also get a 3 on the red and a 4 on the blue. And that's another way of getting a 7. And even though it's the same 2 numbers, it's a different outcome because the dice were different numbers, right? In the first case, the red was a 4. In the second case, the red was a 3. Even though in both cases you got 7 as a total. And so it's important to realize that there's 2 ways of getting a 7 with a 4 and a 3. You can get a 4 on the first dice and a 3 on the second dice, or you can get a 3 on the first dice and a 4 on the second dice. And while both of those are 3 and 4, and both of them give you a 7, it comes about from 2 different outcomes. There's 2 different ways of getting that 7. All right. So let's think of one red and one blue. List the different possible outcomes. Now I'm going to need some space to do this. So part A is basically asking us, what's the sample space here? Now you might say, what the mistake a lot of students make with this is they'll say, well, you can get a 2, right? If you get snake eyes, 1 and 1, that's a 2. You can get a 3, and then the highest you can get is a 12, right? 6 and 6. So they'll say the sample space is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But that isn't the sample space because, for example, getting a 7, you could get a 6 and a 1. You could get a 5 and a 2. You could get a 4 and a 3. There's multiple ways of getting a 7. So 7 is not the sample space because 7 is not a simple event, right? Because 7 can be broken down into 6 and 1, 5 and 2, 4 and 3. And so we have to break these down into individual outcomes from the 2 dice. And so the way I like to do that is with color coding it. So we have a red dice. Now, one possible outcome for the red dice is that you might get a 1. Right? So the red dice, you roll it, you get a 1. Another outcome for the red dice, actually, let me move that further over here. So 1. Another possible outcome is that you could get a 2 with the red dice. Another outcome for the red dice is you might get a 3 or a 4 or a 5 or a 6. Right? Now for the blue dice, you could get a 1 also. Right? And that's the case where you get snake eyes, 1 and 1. Right? But you could also roll a 1 with the red dice and a 2 with the blue dice. And that gives you a 3. But you could also get a 3 by rolling a 2 with the red dice and a 1 with the blue dice. And again, while they're both just 2 and 1, and if the dice were the same color, you wouldn't know the difference. Because we have different colored dice, you realize that this 3 is different than this 3. Even though they both add up to 3, you arrive at that 3 in a different way, right? Here the red dice is 1, here the red dice is 2. And so those are 2 different outcomes that you can get from rolling these 2 dice, even though they both result in a 3 ultimately. All right, so you get the idea that to fill this in, we're going to have to consider every way of getting, every outcome from the red dice and the blue dice combined together, right? So another outcome is that the red dice could be a 1 and the blue dice could be a 3, right? So I'm going to finish filling out this. I kind of think of it like a table. I'm going to pause it though, so that again, it reduces the recording time and you don't have to sit there and watch me. It's going to be a little bit tedious. I don't want to make you have to sit there and watch. So I'll pause it and then I'll resume and you'll see all the results here in just a second. All right, so here are all the possible outcomes of rolling a red dice and a blue dice. All right, so you take every possible combination of an outcome from the red dice, with every possible outcome of the blue dice, right? And you just take every combination of the 2, and this is what you come up with. And you see that there's 36 possible outcomes, right? There's 6 outcomes from the red dice crossed with 6 outcomes from the blue dice, which gives us 36 entries on our table, right? So it's, the number of outcomes of the red dice make up the columns. The number of outcomes for the blue dice make up the rows. So you have 6 columns for the 6 outcomes on the red dice, and you have 6 rows for the 6 outcomes on the blue dice. And so if you have a table that's 6 by 6, that gives you 36 entries altogether, 36 cells, whatever you want to call it. So there are 36 possible outcomes when you roll 2 dice. Now this is true even when the dice are not color-coded, right? Because again, there's 2 distinct dice. So however you want to keep track of them or label them, there's dice A and dice B. And when you roll those 2 dice, there are always going to be 36 possible outcomes there. All right. And so that's A. This is the sample space for rolling 2 dice. Like I said, when you're just rolling 1 dice or flipping 1 coin, that situation stays pretty manageable and people have a pretty good intuition about that. But when you're talking about 2 dice, you maybe didn't realize there are 36 different things that can happen when you roll 2 dice. When you're flipping 3 coins, there are 8 different things that can happen when you roll, when you flip 3 coins, right? And identifying those and just realizing that, it becomes more complicated, All right, what is the probability of rolling a 7 with these 2 dice? So again, we want to calculate that theoretically, right? Because each of these outcomes is equally likely. So we're going to take the probability of rolling a 7 is the number of ways to roll a 7 with the 2 dice. Now remember, if you're rolling just 1 dice, rolling a 7 is impossible. The probability is 0. But with rolling 2 dice, it can definitely happen. So total number of outcomes, right? So we're going to find the number of ways to roll a 7 with 2 dice, and then divide that by the total number of outcomes. And I'm really excited about this result. I think this one's interesting to me. All right, so how many ways can we roll a 7? Well, we could roll a 6 with the red dice and a 1 with the blue dice. That's a 7 right there. We could also roll a 1 with the red dice and a 6 with the blue dice, right? Now, again, I know those are both 6 and 1s, but we arrive at the 6 and the 1 in a different way, right? Here, the red dice is 6. Here, the red dice is the 1. And that's also a 7, right? We could also do 2 and 5. 2 on the red dice, 5 on the blue dice. Or we could have 5 on the red dice, 2 on the blue dice. That's another possible way to get a 7. We could also have 3 and 4. 3 on the red, 4 on the blue, or 4 on the red, 3 on the blue. And so you see, and what's kind of neat about setting up the information this way is that each possible outcome lines up in a diagonal, right? So, and I kind of drew my table a little bit funny, so it's a little bit crooked here, but this is actually the main diagonal of this table. These are all the ways of getting a 7, right? All the ways of getting a 3 occur along this diagonal, right? All the ways of getting a 4 occur along this diagonal. So you can actually see the different outcomes along these diagonals here, the different sums that you can get. So how many ways can I roll a 7? Well, we have 1, 2, 3, 4, 5, 6. There's 6 ways to roll a 7 with 2 dice out of 36 possible outcomes. So 6 ways out of 36 possible outcomes, which I think in this case it's helpful to reduce. It reduces to 1/6, which I think is interesting. It's fascinating because that's the chance of rolling a 2 with just 1 dice. So the probability of rolling a 7 with 2 dice is the same as rolling any particular number with just 1 dice. So 7, in fact, if you look at this chart, is the most likely outcome of rolling 2 dice, right? It has the most ways of happening. Every other outcome is less likely. So rolling a 7 is the most likely outcome. Now, if you play, I don't know if you're nerdy like I am, but if you play board games, maybe you've played Settlers of Catan. And in that game, it's about rolling 2 dice, and you get resources depending on where your settlements are and what number is rolled on the dice. And, that game's infused with probability because, there are some resources that you get when you roll a 2 or a 12, but those are really rare to happen, right? What's the probability of rolling a 2 with just 1 dice? Well, there's only one way for that to happen. So the probability of rolling a 2 with 2 dice is 1 out of 36. Is that rare? Yes. That's less than 5%. And so that is unlikely, right? It's unlikely to roll a 2. It's unlikely to roll a 12. So you don't want to put your settlements near a 2 or a 12 because those numbers are not going to come up very often in that game. But what's also interesting is that 7 has a special, event occur. I don't know how else to say it in Settlers of Catan. So 7 is not attached to any resources. If you roll a 7 in that game, it activates the robber, and the robber gets moved, and you steal a resource from another player in that case. And they chose 7 as that because that is the most likely outcome when you roll 2 dice. And it doesn't always happen a lot in a game. Again, there's variance there. Sometimes you get lucky and 7 doesn't happen very often. Other games you get 7 all the time, right? But they chose 7 to be the robber because it's the most likely outcome of rolling 2 dice. All right. What is the probability of not rolling a 7? So here's a case where using the complement is going to be easier because we don't want to count up all these different ways of not rolling a 7. The easiest way of, especially since we already have the probability of rolling a 7, the easiest way to calculate that is to use the complement. The probability of not rolling a 7 is equal to 1 minus the probability of rolling a 7. Right? And we know the probability of rolling a 7 is 1/6. And so we'll take 1 minus that to find the probability of not rolling a 7. Now, sometimes when students use this complement rule, they kind of get lost. They lose track of where they were headed, and they'll do this probability calculation, and then they think, oh, that's my answer. But for the complement, you want to take 1 minus that probability to get the complement, the probability of the complement. So the probability of not rolling a 7 is going to be 1 minus this, which, again, we did earlier in the video. It's going to be 5/6, right? So that's the chance of not rolling a 7 when you roll 2 dice. All right. So hopefully you found that interesting, thinking about, because rolling 2 dice is a common thing you do when you play games and stuff. And so now you have an idea of how those probabilities work. You have a 5 in 36 chance of rolling a 6, right? There's 5 different outcomes here of rolling a 6. So the probability of rolling a 6, there's 5 ways to roll a 6 with 2 dice out of 36 possible outcomes. That's the probability of rolling a 6. So now you know how to calculate the probability of any particular outcome when you're rolling 2 dice. And like I said, it's not really that intuitive. A lot of people have trouble understanding that, but now hopefully you do. All right, so I think this is my last example, even though I have a couple more pages here, one more with the questions. So this page has the data, which is really blurry. I apologize for that. I think I snapped a picture of it, and then I expanded it in my presentation here, and it didn't seem that blurry when I did it originally, but now that I'm looking at it, it is kind of hard to see. So sometimes you'll get data in charts like this. So the background story here is that they have these subjects that took a lie detector test. And what can be confusing for students about this data is, and I find it interesting because I feel like people just trust the machine. So if the machine says you lied, then you lied. But that is not always the case. And so what we're looking at here is we're splitting up the data based on 2 different characteristics, if you will. One characteristic of these test subjects is whether the machine said they lied. So whether they got a positive test result or a negative test result. Versus whether they actually lied or not. So think of this as like a quality assurance test, right? We're taking this lie detector and we're going to direct people to lie or not lie to see if the machine gives us accurate results. So we're going to look at the results of the machine versus whether the person actually lied or not to see if the machine got it correct, right? So the test results are what the machine is saying about whether the person's lying or not versus whether in actuality the person told a lie. So here we have the people that did not lie when they took the test, and we know for a fact they didn't lie, regardless of what the machine said, right? So these 15 people didn't lie, but the machine said that they did lie, but they actually did not. So there's the actual truth of it versus what the machine is saying occurred, right? So these people, the machine said they didn't lie. Now for these 32 people, the machine was right. These people did not lie, and the machine said they did not lie. And so these 32 people got the result they should have gotten. These 15 people did not get the result they should have gotten. They didn't lie, but the machine thought that they were lying. And those are called false positives, right? The machine gave the machine gave a positive result that they were telling a lie when in fact they weren't. And so that it was a false positive, right? It should not have registered positive when it did. these people actually were lying, right? So these 42 people told a lie, and the machine said that they were lying. And so the machine was correct in this case. But for these 9 people, and these are the people that got away with it, right? They told a lie, but the machine thought they were telling the truth, right? So the machine gave a negative result that they weren't lying, when in fact they were lying. And so those are called false negatives, right? They got a negative result when in fact it should have been a positive result for them. All right. So that's how you read that table. So let's answer these questions. How many responses were actually lies? Right? So actually, not whether the machine thought it was a lie, but how many of the subjects actually lied? That's this column right here. Sorry, I'm looking at the wrong one. That's this column here. Am I doing the right question here? Whoops, I went the wrong way. Were actually lies. Sorry. Okay, so it's this column. I apologize. These are the people that actually lied during the polygraph test. Regardless of what the machine was saying that they did, these people were the ones that actually lied. The 42 people here who lied and got caught, and the 9 people here that lied and got away with it, lied, right? All of these people here lied. So to find the total number of people that lied on this test, you have to add this column up. So we add that up and we get 51. So 51 people actually lied during the polygraph test, right? 51 people altogether. So we have 51. That's the answer for part A. If one of the responses is randomly selected, what is the probability that it is somebody who lied? Right? So we want to take the probability of finding somebody that lied. The theoretical calculation here is you take the number of ways. I don't want to say ways here because it's going to get too verbose. Oh man, I hit the wrong button. I'm just going to say the number of people that lied. The number of people that lied are the number of ways you could choose somebody who lied, right? So the number of people who lied, right? That's the numerator. That's the number of ways you could pick somebody who told a lie, divided by the total number of people in the study, which is the total number of people that we could choose from, right? Which is the number of ways we could choose a person. So there's a number of ways we could choose somebody who lied. That's the number of people who lied. That goes on top. On the bottom, it's the total number of people that we have to choose from. That's the total number of people in the survey, right? So part A is actually the numerator, right? So they kind of walked us through doing this calculation. How many people actually lied? 51. We have 51 ways of choosing somebody who lied because we have 51 people to choose from that told a lie out of how many people altogether? That's the total number of people that we could select, which we didn't compute yet. Now, sometimes somewhere in the table, they will tell you. The background information isn't here, but I think in the background information, it actually says, here's how many people were in the study. How do I find the total number of people? It's not given to me, so I have to add it up. And so you want to add up all 4 of these categories to find out how many people are actually in the study altogether, right? So we have 15 plus 32 plus 42 plus 9. And that's going to give me, I might be able to do it in my head, but I'm just going to use my calculator just to be safe. 15 plus 32 plus 42 plus 9. It's going to be 98. So there's 98 people in the study altogether. We have 98 people to choose from altogether. That's going to be our denominator. Right? So it's going to be 51 over 98, which again, we can just leave as a fraction. I understand that might be bothersome because, again, what's the actual probability there? It's a little bit hard to understand. It's about 50-50, right? But if you wanted to calculate that exactly, it's 52%, 0.52. 0.521, I think, if you go 3 significant. No, 520 if you go 3. I almost hit the wrong button again. 520 if you go 3 significant digits. Sorry, my 2's are looking bad here. Let's just undo those. All right, 520. Okay. As a decimal, if you feel better about having the number in decimal form. If one of the responses is randomly selected, what is the probability that it is a false negative? What does this probability suggest about the accuracy of the polygraph test? So going back to the previous table, false negatives are right here. So these are people that lied and got away with it. The machine did not detect that they were lying. There were 9. So we don't want to add up this whole column. We just want What's the probability of getting a false negative? There's 9 ways to choose somebody with a false negative, divided by the total number of people to choose from, which is 98. So 9 out of 98. So the probability of specifically getting somebody with a false negative result is going to be 9 over 98, which again, if you feel like, is that rare? Is that unlikely? The answer is no, but you might want to see that in decimal form in order to have a better sense of that. This is going to be 0.092. Sorry, 0.0918 if I'm following my rule for 3 significant digits, which is roughly 9%, which is not unlikely, right? So again, many students come to the class feeling like 9-10% would be an unlikely probability, but we are not going to consider those kind of probabilities unlikely. So it's not unlikely to get a false negative with this polygraph. So how accurate is it? It's not very accurate. 1 in 10 people are going to lie and get away with it according to this data. And that's not good, right? And that's not good in and of itself, but that's actually, to me, not the worst situation. The worst one is people telling the truth and being accused of lying. That bothers me more, and that's actually even more likely, right? There were 15 people who didn't lie, but the machine said they were lying. So 15 out of 98, which is even higher than 9%. And so if you look at the number of times the machine is wrong, it's too high of a probability. And so the polygraph machine is not trustworthy, which is why I think in a lot of states it's not admissible. Like polygraph results are not admissible evidence in court because they're not reliable enough. They do get a lot of them right, but they get too many of them wrong for it to be trusted when you're, judging somebody's innocence or guilt. So, all right, so that concludes section 4.1 on the basics of probability. I'll see you in the next video for section 4.2.